This diagram illustrates the standard model of our universe's energy density. We see baryonic matter, dark matter, and taking up the vast majority of the space, roughly 69%, is dark energy. That specific dark energy fraction is not a loose estimate. It is an incredibly precise number derived from an overlapping consensus of modern astrophysics. Legacy data from the Planck 2018 mission, combined with baryon acoustic oscillations, pins that value down to exactly 0.6889 with a tiny margin of error. Yet when theoretical physicists attempt to calculate that density from the ground up using quantum field theory by summing the zero-point energy of the vacuum, the result is off by a factor of 10 to the power of 120. Because the bulk vacuum calculation fails so completely, standard cosmology treats the cosmological constant, lambda, as an observational parameter. We measure it, we plug the number into our models, but we cannot derive it from first principles. We have built our standard model around the majority component whose exact value remains mathematically unexplained. But suppose the answer isn't hiding in the chaotic energy of the bulk vacuum at all. Independent researcher Nadav Bashan proposes a different framework. He treats the cosmological constant strictly as a boundary curvature parameter, a value determined by the geometric edge of the universe. His thesis proposes the dark energy density fraction is exactly pi cubed divided by 45. That equates to roughly 0.689028. Measured against Planck data, the difference is roughly 0.023 sigma. The theoretical output and observed reality are almost identical. A numerical match this tight requires an explanation. We need to trace this specific fraction back to its origin to see if it relies on any hidden adjustable parameters. To find the source of that number, we have to leave cosmological models behind entirely and look at classical thermodynamics. We start with the physics of blackbody radiation, built upon the foundational work of physicists like Ludwig Boltzmann. This equation is the Stefan-Boltzmann law, dictating a spherical blackbody's total luminosity. Unpacking the Stefan-Boltzmann constant reveals foundational values: pi squared, the Boltzmann constant, Planck's reduced constant, and the speed of light. Rearranging algebraically, we move observational variables to one side. In this reduced dimensionless form, Planck's constant, the speed of light, and the Boltzmann constant cancel out entirely, leaving a single pure fraction, pi cubed over 15. This remaining number is the reduced spherical radiative normalization. It is a scale-free geometric invariant. No adjustable parameters, no fitted numbers, just the unique dimensionless normalization of a radiating sphere. Now, we take that strict thermodynamic invariant and apply it to the largest scale possible. We look at the boundary of the observable universe, defined by the kinematic Hubble radius. Mathematically, this radius is simply the speed of light divided by the Hubble constant. Through the work of physicists like Stephen Hawking and Gary Gibbons, we know that cosmological horizons possess strict thermodynamic properties. In a spatially flat universe, this Hubble radius coincides with the apparent horizon. It acts exactly like a thermodynamic boundary. By treating the horizon as that radiating surface, we evaluate our invariant as a fixed boundary condition. The horizon relation becomes the cosmological constant times the Hubble radius squared equal to pi cubed over 15. We now have a rigid mathematical constraint for the boundary of the universe, and we built it without introducing a single new fitted parameter. The final step is translating this fixed boundary relation into the actual dark energy fraction that astronomers measure. This is the standard Friedmann equation for the present dark energy density fraction. Notice the factor of 1/3, a standard geometric factor inherent to the Friedmann definition for a spatially flat background. We substitute the definition of the Hubble radius, the speed of light over the Hubble constant, and plug that resulting expression into the Friedmann equation. The 1/3 multiplies against our geometric invariant, resulting in pi cubed over 45. Because a spatially flat universe requires the total density to equal 1, the corresponding matter density fraction is simply 1 minus pi cubed over 45, giving us 0.3110. If we treat the universe's horizon as a strict thermodynamic boundary, the observed dark energy density partition we measure today is a direct mathematical consequence. We can now return to the observational data gathered by our space telescopes. This chart shows the direct numerical comparison. The theoretical boundary relation gives us 0.6890. The legacy Planck dataset gives us 0.6889. This level of precision is achieved through purely geometric normalization. There are no numbers to tweak. It is important to state the limits of this theory. This is a phenomenological relation. It does not provide a microscopic derivation of dark energy, nor does it attempt to map the full expansion history of the cosmos. We still lack a full quantum mechanical solution to the vacuum energy problem, but the data shows that the late-time density partition is strictly dictated by boundary geometry. There is one final structural check. Does this macroscopic boundary relation violate microscopic quantum mechanics? This is the standard definition of the horizon state count, the horizon area divided by the Planck area. We rewrite our boundary relation using this language, resolving the macroscopic scale into discrete Planck areas to achieve algebraic closure with the gravitational constant. This is not an independent derivation of gravity. It is a proof of consistency. The macroscopic boundary curvature and the discrete microscopic state count remain perfectly algebraically linked. The order of magnitude gap in the bulk vacuum remains unsolved. However, the precise dark energy fraction we observe is not a random error. It is the exact parameter-free image of a perfectly spherical thermodynamic boundary.